First, I would like to start with learning path. If you are a student or working professional from classical world and you want to pursue quantum computing as your career, you have to follow a specific path. You should first identify the domain, in which domain you are going to build quantum computing solutions. I have listed finance, cryptography, QML hardware, but there are many. For example, mechanical, civil, electrical, biotechnology, commerce, MBA, or economics, and weather forecasting, environmental, and supply chain management, logistics. These are all various domain which can benefited by building a quantum solutions. There is a reason why these domains, why not a simple database management system, or why not a billing or any financial accounting. Why don't we use quantum computer or financial accounting? That also we can consider domain, right? See, that clarity you should get. We can use quantum computer only for some certain domains which are having a complex exponential problems, which we generally call them as a NP hard problems. So that you have to identify first. You need not to be expert in the domain, but you have to identify this is the domain I want to work. For example, if you take in my case, I'm a software engineer, then become a data scientist, worked in Dell for 10 years. During that period, I realized that my machine learning, AI, data science knowledge can be applied into quantum machine learning. So I chose quantum machine learning as my domain and then logically progressed into quantum career using quantum machine learning. Like that, you have to identify. If you are a mechanical engineer, you can plan quantum optimization for your domain problems. Like if you are an automotive or aerospace or machineries or heavy what is called heavy engineering systems, those optimizations. Or you may be a civil engineer, you may want to perform the structural analysis or um, risk analysis or structural, all those things you can use quantum computing. Or you may be um, the economics researcher who wants to build Monte Carlo simulation. That is the important point. First you have to identify domain, then anyhow in the solution building you are going to work with a researcher, a physics, a master or doctor in physics. You are going to work with the researcher, so they are going to talk about quantum mechanics and then optics and subatomic scale, nuclear physics, atomic physics, those kind of things. So at least you should get 8,000 to uh, 10,000 to 8,000 level of depth of information or knowledge in physics. Then in your team you will have a mathematician who is very strong in linear algebra, complex number, Hilbert space probability, and complex analysis or functional analysis, real analysis, these kind of mathematical concepts. So since they are part of your team, you are going to interact with them. You have to understand what they are talking, because the mathematician is the person who is going to give the mathematical model, and as a software engineer you are going to build a software solution for the mathematical model. So you're closely going to interact with mathematician. So you have to understand 8,000 to 10,000 feet level of knowledge in mathematics. Then if you are a software engineer, obviously you will choose, this is your vertical, computer programming is your vertical. You can choose Python, C++, Julia. Most of you will start with Python, nothing wrong in it. But my personal recommendation, don't assume that Python is the implementation language. So be prepared to learn C++, Julia also. So this one will give you a clear picture for you where you can understand the learning path involves four vertical: subject matter expert, a physics researcher, a mathematician, and software engineer. Now, based on your qualification and based on your educational stream and based on your interest, you will fall into any one of these four. That you should be very clear. This is my area. So even though this is my area, I have to learn little bit about other area also. Then only you can form a team and then work with the team to build the solution. I will stop here. If okay, I think 9:30 you are starting the Q&A, right? Let us move on to next.
Yeah, yeah,
Now you realized this is the learning path. What you are going to do? Obviously, you should understand what is the feature of quantum computers. Now this is the report from Boston Consulting Group. They um, did the market research, industry research, scientific research, observe the market, observed the invention discoveries. Based on that, they gave a report telling that 2018 to 2028 will be first generation of quantum computing, meaning that it is non-universal and low complexity simulations are developed. But in 2028 to 39, much faster, sophisticated, we can start implementing simulation. But 2031 is 42 is the period where quantum computing will be used in real business problem, industrial problem, use cases. So now it is very clear. If you are starting in 2025, I cannot promise that you will get an immediate job offer immediately. For example, um, you are a undergrad going to third, maybe third year or fourth year now, finishing your college studies immediately. Can you get quantum computing career? Yes and no. Again, it is a superposition of possible possibilities. You can get job and you cannot get job. The reason is multifold. The industry is in the first generation, so there are job requirement, but the level of knowledge and hands-on experience required is more deeper than the classical world. So the selection process is very stringent. They will check whether you have real quantum computing knowledge or just attended some few sessions and then you are interested in the subject and then talking, meaning that 10,000 feet level. Nothing wrong in it. That is a starting point. But you should realize the industry is looking for people with a deeper knowledge. So to gain the deeper knowledge, there are few things what we will discuss later. So that is the thing you have to establish yourself. Now you may wonder where or what are the various branches of quantum technology: quantum network, quantum material, quantum chips, computing, simulator, like this goes. And if those who are watching the national level um, engagement, you will hear that Government of India under the National Quantum Mission identified four verticals: quantum computing, quantum communication, quantum sensing, and quantum materials. These are the four feature of quantum computing. I am observing this industry since 2004, and I am very confident that in couple of years, now it is 2025, right? 2026, 27 and all, you can find lot of opportunity for undergrad. But you should build a strong network. And this QuCode, this 21 challenge is a really good starting point. I really appreciate who are taking part into this one. It is really good initiative to build your quantum knowledge. So first learn, then try to build the network, then find the job. Try to find the job. Don't ask the job on the first meeting with anyone. You understood, right? Because you have to get clarity. What is the expectation in the industry? Prepare according to the expectation, then the job will automatically will reach out to you because the industry is looking for more resources. Now it is my duty to explain what are those problems, because we understood the learning path and also we convinced that quantum computing is a great feature. But what are the problems? Because I told the domain, right? So in domain, you have to understand what are the actual applications where we are using quantum computing. Because if the challenge in quantum computing career is not the solution, it is about understanding the problem for what you are building a solution. So as I told you, classical systems are good at solving um, polynomial time problem, but there are some problems which are not possible to be solved by a known time or in a polynomial time. For example, breaking a cryptographic key. See, that's why we are confidently using our ATM pin and then using passwords, securing our information. Why? Because the hacker cannot easily break the security cryptographic key. Why? Classical computers are going to take non-polynomial time, meaning that to break 2048-bit RSA key, a classical system is going to take years, more than 10 years or 20 years. That's why we are confident enough to use the security system using RSA or AES or DES or EC. These classical cryptographic systems are exponential problem for classical systems. But a quantum computer with a different mathematical model, it can, how to say, it can find the factor of very large integer in a polynomial time as per the Shor's algorithm. Like this, there are many problems. One is AIML, for example, principal component analysis. In computational chemistry, finding the energy level of molecules, and then drug design and development like protein folding, protein prediction, mm, drug behavior, it is called uh, drug treatment, all those drug discovery, yeah, that is those things. Then cryptography and cyber security, meaning in the cyber security we discuss quantum communication, how an entangled photon or a photon in superposition can promise is the most secure form of communication. And um, Sumit is the right person to talk about that one because he is working in QNU Labs, who are uh, one of the uh, early solution provider in quantum technology. QNU Labs started 2016. It is a legacy they are having. So in the cyber security and then quantum communication. Then the financial modeling like derivatives, feature and options, optimizing portfolio, Monte Carlo simulation, then logistic optimization, weather forecasting. Here the weather forecasting is not just a complexity only. It is not exponential problem alone. It is the accuracy of input data. Because when we are doing weather forecasting, you say classical system. Classical systems are binary. So if you measure the property of nature, that will be approximated such that the number is represented as a or approximated into a binary number. Then we are feeding into the system. So what happens? A forecasting system is getting input which is approximated. So garbage in, garbage out. So weather forecasting is a different problem because some of the arguments about the feasibility of quantum computing start like this. Maybe the earlier classical systems are not fast enough, but now we have GPU. GPU are very fast. Still, whether AI/ML problems need a quantum computing. So not only exponential problem. If you need input data without approximation, that time also you have to use quantum computer. So there are two reasons. One is exponential problem, other one is input without approximation. These two things will clearly explain quantum computers are suitable for certain class of problem. And one important thing what I would like to tell, quantum computers will not replace classical system. It is always going to be CPU plus QPU, meaning that classical processing unit working in association with quantum processing unit. So quantum systems will not replace your classical system. For example, database management system, networking. I'm not referring communication, networking, and image processing, video processing, gaming, and just displaying input output, IoT. All these problems are going to stay as a classical system only. Only the mathematical operations, the heavyweight computation, that will be moved to quantum processing units, right? And so if you decided to learn, so these are all popular quantum computers already you may be knowing, but I'm keeping here just to give you the confidence that you are learning something which is in the market, not in the lab. Maybe if you try 5 years earlier, still it was in lab, but now quantum computers are in the market. And this is what the principles of quantum computers. Quantum computers built on principles of quantum mechanics, and they are based on linear algebra of complex numbers. The building blocks is qubit, and they are operating at the subatomic scale. That's why quantum computers are very costly, $15 million to $40 million. So now you may be interested, what are the quantum mechanics? So there are three behaviors: superposition, entanglement, and interference. I'm not going to explain this now because I'm expecting few questions on these topics. That time I will explain. And you can see there are some mathematical formula I wrote for superposition and for entanglement. These things I will explain during the Q&A session. And this one is very important. Not only these five types of computers: superconducting, trapped ion, photonic, neutral atom, quantum annealer. Not only these five, there are other platform also. Scientists are researching, but as of now these four are matured. We are able to build system, but in future we don't know. Maybe NB center in diamond, that may give you a room temperature photonic quantum computer. Then this one is very interesting, I will talk about during the discussion. And this is the architecture of a quantum computer. You can see most of the quantum computers are hanging like this, right? A rooftop structure like chandelier. It is because superconducting quantum computer processors need to operate at microkelvin, which is minus 273 degrees Celsius. And that is also one reason why superconducting quantum computers are very costly, because they need a cryogenic engine for their dilution refrigerator. But other layers can operate in a different temperature. That's the reason why their layer structure, and then they are hanging from the rooftop. This is a short introduction or comparison of classical and quantum technology. You can see here the quantum computer as of now in the nascent stage, they are like small baby compared to a monster like classical computer. But when the technology matures, and then more invention discoveries are helping to build more stable quantum computers, and then more number of qubit, and then reduce the error rate, then quantum computers will become very powerful for selected problems. And keep on telling, quantum computers are good at solving selected problem, not all problems. That's the reason why I'm reiterating it is CPU plus QP. And this is a timeline. I'm not going to talk about this now. And this is the current market. And then you see this 2022. But as of 2025, this is very crowded. But still, this will give you the clear picture. There are really Many organizations, Fortune 500 companies, are exploring quantum computing either as a hardware or GPU or software or end user. So you see, the end user list is very interesting. We have Airbus, BMW, JP Morgan, and AstraZeneca, Denso, Johnson Electric. Like this, there are diversified organizations are exploring quantum computing. Why? Because that is what the domain comes into picture. Then this is the national efforts in our India. The national quantum mission is one important thing. Apart from that, this one is prior to the NQM came into effect. You can see there are government organization, then startups, service providers, and academia. It is a good integration of various organizations to build the quantum technology ecosystem in India. That is one reason we can be very confident that when the industry matures, we will have our place in quantum technology. And this is the investment as of 20. I will get the 2024 data and then update it because still it is need to be. This one is coming from QRECA website. Expecting them to release the next one soon. I will update this chat. But I know the it is around 47, 48 billion as of now. Now you may have an idea, okay, this is cool, this is industry is growing, there is a government support, there are a lot of organization, and what I'm going to learn or how to start. So first you have to start with the software. If you are a strong physics person with hardware knowledge, or electronics and communication, or electronics and instrumentation engineer with a strong physics knowledge and interest in hardware, you can pursue quantum hardware. To be honest, quantum hardware is a great career compared to quantum developers. Quantum researchers and quantum hardware is a really a good career. But I observed most since the word quantum computing, most of the computer science professionals are also pursuing quantum computing. If you are coming from computer science background, obviously you have to start with the software, and these are all the various frameworks. Most of the beginners will start from IBM Qiskit, but my case is different because when I started quantum computing, there is no IBM Qiskit. So I started with a simulator called QCL, Quantum Computing Language, which is like a C++ kind of language. That is one reason maybe I started with the QCL. My preferred framework is QLAX and QEra and Penny Lane. In addition to Qiskit, I'm not using Qiskit. Qiskit is also one of the fundamental, but my preferences are something different, not just to Qiskit alone and Amazon bracket also. For you, I suggest start with IBM Qiskit. Then these are the cloud platforms through which you can access quantum computer because as I told you, it is $15 million to $40 million. Not everyone can afford to buy a quantum computer. So obviously, we are accessing the quantum computers through cloud. As a one input, I can tell you, IBM is offering their quantum computers through cloud for 10 minutes free per month per user. After the 10 minutes consumption, IBM is charging $96 per minute. Something similar to the charge both Amazon and then Azure are charging. Google is not releasing their system for public. It is only for engaged clients only. So actually, after learning this programming framework, getting access to this cloud, what are you going to do? You are going to build quantum computing algorithms because we are in the first generation, correct? If you are in second generation or third generation, we can directly build the solution. But now, being first generation, we should know all the basic quantum computing algorithm, and I strongly recommend learn in the order what I have given. Then some applications algorithm, predominantly optimization algorithm like QBO, QAOA, HHL, VQLS. Then comes quantum machine learning. Then there are many books, and this is my favorite recommendation to watch this movie. With this, I am finishing my presentation. Remaining 1 hour will be Q&A session. Okay. Now I'm done.